As we want to move into this, continue on, I should say, with the E&M theory stuff that we looked at yesterday. I'm going to try to do some recording of this with the webcam that's embedded so that people can see demonstrations if they're gone. So yesterday, is it true we got through the stuff that I have listed up here is what we covered yesterday? Yeah, we haven't done any applications. That's where it takes demonstrations here. I want to reemphasize that we talked about the right-hand rule. So yesterday we were looking at the right-hand rule. The thumb goes in the direction of the current. What kind of current, refresh my memory, what kind of current is that? Electron current or conventional current? It's conventional. And so that's the way we typically draw things on there. The right-hand rule, which is what we see there, has to do with conventional current. Of course, if I had electron current, I'd just use the left hand. Right? We'd get the same direction. Okay. We talked about line density, and that becomes an important thing. So when I talk about the magnetic field, north and south, refresh my memory, which way did it go? Goes from north to the south. They're always closed loops. And we talked about line density. The more dense those lines are in a region of space, the stronger that magnetic field. I lied yesterday, and I'm going to go on record that I lied to you. Even I make mistakes. I told you that the magnetic field falls off at a rate proportional to the square of the distance, didn't I? I lied. It's not proportional to the square of the distance, and the reason it's not is because that magnetic field does not radiate spherically. It radiates in a circle. Do you guys see that? So the magnetic field actually falls off at a rate proportional to the distance. So it'd be over a 2 pi r instead of a 4/3 pi r cubed, or 4 pi r squared for surface area, right? So that actually falls off at a rate proportional to the distance, not proportional to distance squared. Remember that whole inverse square law had to do with spherical things. That magnetic field, you guys see those things are in a plane going through a circle? Does that make sense? Okay, so I lied yesterday, and I was looking through the various equations that we're supposed to be covering in this unit. I'm like, oh, wait, it's over an r, not an r squared. So my apologies. All right, let's take a look at the electromagnet. Now, the electromagnet, I had kids do this yesterday to be able to, in my one semester class where they built an electromagnet. I'm not going to have you guys do that lab just simply because we don't have time for that, but I can show you how that basic thing operates. So we have a magnetic field that's generated by the electrical current. We can magnetize that iron nail to be able to have a temporary magnet. As long as I have current flowing, I can use that current to be able to create a magnetic field and then use that to be able to do some things like lifting up. Not just paper clips. A common application of that might be a junkyard where someone has to move a car from one point to another, and they use an electromagnet to lift it up, and then they de-energize that electromagnet to drop it. I'm going to demonstrate a force being exerted on a wire through magnetism. I'll do that with the horseshoe magnet that I have up here. And then also I want to be able to look at a motor setup. So how we generate mechanical motion from electricity is through this process of a force being exerted on a wire that has current flowing through it. And then the speaker, I don't know if I'll do this demonstration today or not, but you guys will build a speaker. I'd like to have you see how a speaker works and have you build it. It's not too bad to do. And I don't know if I'll do that demo again today or not. I'd like to do it when people can actually see it as opposed to doing it on a video. All right, so I'd like to show you first just the force being exerted on a wire. So I'm going to try to do that with this video. And so Jack, you're really close to this. So if you don't want to be a part of that video, you might move away a little bit there. Okay. So horseshoe magnet, Jack, maybe you can help me. I'll put that horseshoe magnet on its end.
This?
Nope, other way. So one side is the North Pole, one side is the South Pole, right? And so what I'm going to do is I'm going to run a direct current through that coil. Okay, so a direct current through that coil. Now, a direct current means what about those charges? How do they flow? Direct. One direction, correct? One direction. So I'm not sure exactly which way that thing is flowing because of the color schemes there and stuff like that, but it's going to be constant. So if it's flowing clockwise through that, it's going to create a magnetic field. One side would be north, the other side would be south. Now there is a permanent magnetic field from that bar magnet. When I turn this thing on, I'm going to go ahead and turn this on a little bit, you might see that I can generate a force on that wire from the magnetic field that's a part of that permanent magnet. So sometimes it works, sometimes it doesn't. So I'm going to go ahead and turn this thing on. And you can see that I'm able to lift that up. And I'm lifting that up through the magnetic field that's being generated around that wire. That force comes from what? What object is exerting the force necessary to lift up that wire? And you can see it. What's the object exerting force on that wire to lift it? Turn and tell that person that you're sitting next to. Remember, all forces come in pairs. There's always two objects involved in every force pair. What's the object that lifts up that horseshoe or that wire? Tell that person you're sitting next to. You guys, say it again, Scout. The magnet that's there. That magnet has a permanent magnetic field. One side is north, the other side is south. Now, when I run that current through that wire, it creates a magnetic field around that wire, and that interacts with the permanent magnet to be able to lift it. So, try that one more time. I increase the current a little bit. You guys see it lifted up a little higher? What will happen if I change the pole that's inside of that coil? What will happen now? Turn and tell that person that you're sitting next to. I flipped it from I had it like this. I flipped it like that. What's going to happen? What's going to happen in this? Don't be shy. You're not being recorded. Like, well, your voice is, but no one knows it. Same thing? Everyone agree? Exact same thing? All right, let's try it. Now, what I notice when I do that, you guys notice, what's it trying to do? Trying to push it down. And why is that? Because the direction of the magnetic field is the same as it was before because I haven't changed the direction of current. But I did change what the pole was, right? How can I get that thing to lift up now? I'm going to change the direction of the current, right? So I'm going to flip, you guys can't see this, but I'm changing the red to the black. I'm just going to flip those around. So now I'm sending the current the opposite way. Let's try it one more time. What's going to happen when I turn it on? It lifts back up. You guys see that? All right, what's going to happen if I put an alternating current through it? This is direct current. What's going to happen if I put an alternating current through it? You're not going to die, no. Say it one more time, Peyton. It's going to oscillate. Now, the problem is that the table stops the thing from going down, correct? This table stops it from going down. So you're not going to be able to see it oscillate really well because of that. But if I switch this over from the red and black, I put it to the yellow terminals. You guys did not have to do anything with the power supplies in the yellow terminals yet, right? That's the alternating current. Well, do we talk about alternating current when we were doing the electricity stuff? AC, like when I plug into this outlet here, it's 120 volt AC. The person that won in the current wars was Tesla, Westinghouse, because it was AC, not DC. That's important. The fact you guys didn't get to see it. Juniors that were doing the testing, I showed a movie called The Current Wars. It's really good. Would you guys agree? Yeah, it was good. All right, so I'm going to flip this thing over to the alternating current. Turn that thing on, and now you might be able to see. Jack, put your hand on that. Can you feel it vibrating? Yeah. Yeah, it is vibrating. Vibrating at about 60 hertz. 60 is like, why is it getting hot? Because the only thing that's dissipating heat or dissipating energy right now is the resistance to that wire. And that wire has resistance, but it's pretty small. So I'm running a lot of current through it, right? So I'm going to try it like this. So now at least we can sort of see what it would look like if it doesn't have the table to be able to go through and do that. And Jack, again, you can't really see it oscillating because it's oscillating so quickly, but it is vibrating, right? You can feel that. Okay? Say it again. You can hear 60 hertz, but it doesn't produce a lot of sound because it doesn't have a lot of surface area. I mean, I guess I might as well just show you guys this here. I'm going to show it to you. I'm going, ouch, that's hot. All right. You guys want to see this a little bit closer? Come on up for a few minutes. And so, yeah, just come on up over to this spot. I'm gonna get this stuff set up here so we can see it. The people that are permanent, that magnet, those are neodymium magnets. Jack was trying to push those things together and hold those apart yesterday. They're very strong. And so what will happen when I run a current through this, I'm going to put an alternating current through it. You should see that this coil will go, this thing will go up, it'll go down, it'll go up, it'll go down at the frequency that is being driven by the electrical current being provided. Okay? So I'm going to try to get this set up here. I'm going to put it at 1 cycle per second. Now you guys can't see that, but I'm going to run this thing at a 1 cycle per second. So every second it's going to go through its cycle. And we're going to see what that does to this thing here. So just got to connect this up. Jeff, can you help me with that? My fingers are not good at connecting those things.
The coil is already cold.
Yeah. Okay, so we're gonna try it. Now let's just see. No. Edit this video. Okay, now you can sort of see. Now that magnetic field is strong enough from that coil that's actually lifting up that magnet underneath. Can you guys see that? Okay. Now I'm going to increase the frequency. That's 3 cycles per second. That's 4. Can you hold the base? Hold it from one side, not the other side, so we can see the other side. There you go. That's 9 cycles per second. That's 10. That's 20 cycles per second. Now what you're hearing is a lot of rattling from that speaker that's going down. I'm going to start going up by 10s now. That's 40. That's 50. That's 60. That's 70. That's 80. That's 90. That's 100. That's 110. Can you guys hear that? Right now that's 500 hertz. Can you guys hear it? Jack, feel that thing. It's vibrating, correct? How many cycles per second is it vibrating at? 500 cycles per second. You guys can hear that. Let's go up by 1,000.
You make it play a song.
Can I make it play a song? That's interesting. That's 2,000. That's 3,000. That's 4,000. 5, 6, 7, 8. Can you guys still hear that? 9. I've lost it. It's gone. Can you guys hear it?
Yeah.
That's 14,000. Can you guys hear it?
Yeah.
All right, then turn it off. You want to play music with it?
Yeah. Try it.
We'll try it. All right, grab my boombox over there.
I don't know if it's going to work is the question.
I don't know. I've never tried this before, so I'm not sure. All right. So instead of connecting this up to the function generator, I'm going to connect it up over here. And so Jack, you're gonna help me with this. I need those red and the 2 red cables there connected to that there. You just have to sort of wrap those things around.
So it doesn't matter which one.
Not really, no. Okay, so we're gonna try it. Makes for good video if we have all. I got to get rid of all of the lag time on this, right? Anyone have like a good stereo system at home? Yeah. You can make a speaker out of just paper. You don't need anything really fancy. The music quality is actually pretty good. All right. So
You got one attached.
you got one attached. All right. So let's give this a shot. Now remember that magnet that permanent magnet that's in place. That permanent magnet that's in place is the thing that's exerting force on that paper. See if you can get that so that we can see the magnet. Okay. So yep, that works. Now I'll try it. You know this song? Feel the top. It's vibrating. Much more complex than a sinusoidal waveform, but it's vibrating. And that electrical signal, if I were to look at it going to the speaker, would be much more complicated than just a sine wave, right? So yeah, let's give it some bass. Oh, it already has bass. I'm going to take the bass down. I'm going to take the treble down. You guys notice that the treble sort of, do you guys hear the difference in sound? Okay, that's the 10,000 to 20,000 hertz range. This is the 1,000 to 10,000. And this is the bass. It's not bad. It actually does a pretty decent job of producing sound. But it's just paper.
How loud can you make it?
That's about as loud as I can get. There's distortion, right? There's distortion. A little, yeah.
Well, it starts shifting out of frame.
So it's amazing. Are you guys amazed at how simple a speaker is? People don't realize it. It's like, oh, it's in relationship to
So much.
well, so the distortion that you guys heard, like I want to be able to play music loud and not have distortion. That takes, I mean, we're just making this out of paper, right? But if you're going to actually make something, the cone itself has to be something other than paper. This portion here is like a spring, right? Jack, show me the spring portion. Put your hand on that. That's like a spring, right? It's got restoring force. We studied simple amount of force. That thing's in a state of equilibrium, and then when I cause it to distort because of that magnetic field, it wants to return, right, to that equilibrium position. And so, yeah, that's it. Pretty cool.
What happened if you fix the magnets in place without changing it?
Yeah, that's
So you guys noticed that when it was 1 or 2 or 3 or 5 hertz, it was so slow that it caused the whole magnet to come up. Right now, the vibrations are so small that it doesn't have time really to lift that magnet up. You could, if you take that magnet and you glued it to that base, it would probably work a little bit better. But then I can't disassemble it and sort of that. So that makes sense. Yeah.
Could you just magnet to the bottom, like underneath the paper, and then in here and put it over the edge?
Okay, so what's going to happen when I take away the magnet? I mean, I'm still running electrical current through that wire, but there's no ability to exert force. Jack, go ahead and just bring that thing close to it. Don't put it inside that coil. You can feel the sound, right?
Yeah.
But it's got to be inside that coil to be able to get the strongest interaction, right? Okay, put it back in. Pretty cool. All right. Well, I was going to do that tomorrow, but you guys were so excited to be able to do that. That's awesome. All right, let's head on back. Wait till you guys build it yourself.
What is that?
I'd like you guys to be able to do it. I might have to do it honestly. My goal is to get done with this by Friday of next week. And the reason for that is after that, what happens the week after Friday of next week? A lot of AP tests. And so my goal is to be done with this unit by the end of next week. So what I do at that point, folks, by the way, is I do a lot of more what's called independent study kind of stuff, where I have lectures and everything. I've recorded video lectures on about optics and stuff like that, but it's much more independent work because Trayson's going to be gone for the AP Calc exam on this particular day, and Aiden's going to be gone for the AP Physics. I mean, it's all over the place. It's like 2 weeks of just mayhem. And so what I do at that point is I say, all right, here are some projects for you guys to work on, and you do it based on when you're here, right? And so one of those would be like build a speaker. Okay, that's sort of the plan. Okay, cool. I'm glad you guys enjoyed it. All right, next piece of evidence. Evidence that electricity and magnetism are intertwined. A changing magnetic field produces, this is evidence number 2. A changing magnetic field produces an electrical force in objects that can produce current. So if electricity can create magnetism, this is showing that magnetism can create electricity. Remember, E and M are like two sides of the same coin, so they can coexist. They often will create each other. The application of this is the opposite of a motor. If a motor takes electrical energy and converts it into mechanical, what's the opposite of that? Takes mechanical and turns it into electrical, right? So the main application of this is a generator. So generators are sort of the opposite of a motor. So you guys had actually I'm wondering, when you guys did the the lab on optimization, when the mass was strong enough to go back down the hill because it was heavy enough, did you guys notice that the current reading on the ammeter would fluctuate a little bit as it was doing the work necessary to run that motor? Did you guys notice that? If you didn't notice that, that's basically a motor and a generator are opposite of each other. In one case, the electrical current is driving the motor to run. The other case, the motor being run by mechanical load is causing electrical current to be created. That's the opposite of this other one here, right? So if electricity can create magnetism, this is showing magnetism can create electricity. This is a hand crank generator. This is a steam generator. This is something right out of X-Men, a magnetohydrodynamic generator. Again, it's just ways of generating electrical energy from mechanical work. The last one is more about flowing charges that are going, it's like a beam, if you will, that's going through a horseshoe magnet, and we can separate up those charges, put them on those two different plates, and essentially have like a little battery. Okay, so those are, that's number 2. Number 3 on the list is the thing that gives me concern. It's the what's called mutual induction. So if electricity can create magnetism and magnetism can create electricity, there are applications where we rely on mutual induction. And the most common one is the transformer. And we'll finish this unit by looking at how transformers are designed, why it is that the transformer was critical to us having AC current as opposed to DC current be the lifeline of our electrical infrastructure. So we'll study that in detail, the transformer. Those little buckets that are on the telephone poles that you see there are transformers. This is the Aurora Borealis, the Northern Lights, pretty cool. Have you ever seen them? Raise your hand if you've ever seen the Northern Lights. First, why do they call them northern? Because they're usually in the north sky. It has to do with interactions between solar particles coming from the sun and the magnetic field of the Earth.